Hello there. Let's get started on studying electromagnetic waves today. So we are just going to touch on basics and where the comes, how it flows in empty space, some simple solution, and how the energy flows. We're not going to address the question of how it gets generated. How do you get the waves produced? For instance, quantum mechanically, they're produced by actually jump from one energy state to another energy state. But classically, which we're going to do, we're not going to do quantum mechanics. Classically, they are produced by accelerating charges. We're going to see that, for instance, in antenna, where the radio waves you're familiar with, like radio and TV and things like that, they get generated in antenna when charges flowing back and forth, accelerating charges. And switch electrons move up and then switch direction and then move down, switch direction. And we are going to address that maybe a few weeks from now. But first, we're going to learn what a wave is and how electromagnetic theories actually tell us that there has to be a wave, and that was one of the biggest achievements of Maxwell. Okay, so that's why. So we're going to learn the basics, how to characterize a wave, some basic properties you may already know because some of this already gets covered in very elementary science courses. But this is not. This we're going to learn because that's where the physics course should address, because we learned all the electric field, magnetic field, and what kinds of equations they should obey. Okay, and then those equations have a very interesting solution called plane wave solution, and there are other solutions as well, but the plane wave is a very simple one, and you can build your understanding, almost all the understanding of any type of wave that you can encounter. You can build it from plane wave through a process called Fourier analysis. Okay, but we're not going to go there. We're just going to learn the plane wave solution, and then this is very important. This usually is a very high consideration, how energy actually flows. If the wave is moving, how much energy is passing per unit time. So suppose you have a collector of some place where the waves are hitting, and the question is how much energy it's depositing, how much momentum it's depositing on whatever thing the wave is going to hit and get collected, so absorbed. So suppose you have some absorber of the wave, then what's going to happen there? I'm not going to address the bounce off, this, that, but just the energy part, how much energy is carrying. So we can use the energy conservation to say how much energy must be hitting this final target. Okay, it's kind of like when you hit a bullet, the question is how much energy the bullet is carrying, right? And so in same the case, how much energy the flow of the wave is carrying. So that's an important question, and we're going to address that, and could take us into something called pointing vector, and we'll learn some ways to quantify it, not just talk about it qualitatively. Okay, so let's get started. Okay, so when we talk about waves, we have in mind something. It's just kind of rough drawing, right? So some property which is fluctuating and it's kind of moving in some direction. So it's a qualitative view of the wave. We can assign that say this is at some particular time t, the wave looks like this and it's moving. By moving, we'll say, if I look at this a little bit later time, the wave is, so this is a t plus delta t. Now you can say that eventually the wave will just keep moving. It's going to this yellow will meet over there, and so there can be a time for repeating this. So this distance, we purposefully put a repeated thing, so this is going to repeats it. So this repeat is called wavelength in the distance, and the time it takes so it's eventually it's gonna come down and go the white one that I wrote down. So repeat distance is called wavelength, and if it's moving at if it's light, then it's moving at the speed of light c. So it's going to repeat time is called period, and it's going to repeat in, say, period it's going to repeat in time lambda over c. That's going to be the time it'll take to repeat. And so how many times it's the inverse of this period, so t, inverse of the period is called frequency. This is how many times it's going to repeat per unit time. So number of repeats is this, and this is called frequency. So if you can see so c over lambda, so frequency will be c over lambda, and so you can see that lambda wavelength times f is the speed, and this is called fundamental equation of waves. This is fundamental equation, and can solve a whole bunch of problems just using this fundamental formula of waves. You should memorize it. Sometimes people memorize it, just call this V. Okay, so instead of speed of light, this could be true for sound wave, other types of waves, matter waves. So whenever you have a wave, you have a wavelength and a frequency associated with it, and there may be multiple frequencies associated with a wave, but we're talking about wave of one frequency, sometimes called monochromatic waves. So this is always the case for a monochromatic wave. Okay, I hope that's all clear to you. Okay, so when you look at electromagnetic waves, you have h times f is its energy. So the energy of a wave, energy of a photon in that wave, em photon is h times f. It's not the energy in the wave, but energy in the wave consists of energies added up of all the photons. A classical wave has many photons, and it's not possible to have to count all those photons. There are way too many in classical waves. So when you do a quantum experiment, you actually bring it down to a few photons that you can study, like 1 photon, 2 photons, 10 photons, 5 photons. You just few photons, then you can study the quantum state of the photons. But we are doing the classical, and then in the classical we have this is just as a representation what it would look like if I were using in terms of photons. So photons in the waves of electromagnetic waves will have energies like this. So in quantum, you usually use units called electron volt for energy. So one electron volt is electron will charge of electron, and times volt, 1 volt. So this will be 1.6 times 10 to the power 18 joules. It's not 18, I misremembered. It's 19, 10 to the minus 19 joules. Okay, and that's the charge of electron in coulomb. So it's very small amount, but that's not the energy of an electromagnetic wave. It will have many photons, and then there will be a millijoule and things like that. Okay, all right. You looking at the it's a really nice way. This is coming from Loren and Carson. I found this to be a very nice way of writing things. Instead of writing actual values, you write 10 to the power, just the power thing, and you display it in this exponent. Okay. For instance, this will be like a 10 to minus 6 meter, and so this will be a micrometer. And you can see that this whole thing is presented that you can actually draw lines and to figure out other properties like frequencies, frequency, wavelength, and energy for that particular wave. And important to notice that visible light is very small window, just a very tiny window here. This is visible light. Okay, and so it's like this will be like 1 electron volt. So near 1 electron volt, because log of 1 will be 0. A little bit more than 1 electron volt, 1.2, 1.5, right? So it's over here, and if your wavelength is this side is wavelength gets bigger, and so this side is larger wavelength, and so this is a smaller frequency, and this is larger frequencies and smaller wavelengths. You can see that 10 to the power, like this is like a size of an atom, right? So size of an atom will be 10 to minus 10 over here, size of an atom. So you have all these gamma rays, which is actually way smaller than the size of the atom. And gamma rays, it's hard to tell from the gamma rays if they're waves or not, because the wave property is pretty hard to detect, right? You only detect like gamma rays as rays and particles, and X-rays. X-rays go, overlap the ultraviolet and continue on. All right, so this is like a basic description of the waves, and let's move on to the Maxwell's question. How do we know that these kinds of waves exist in just from the Maxwell's equations? That there will be a wave traveling with the speed of light, just the Maxwell's equations. Okay, let's write out Maxwell's equations in vacuum. So Maxwell's equations are recall Maxwell's equations are for electric field del dot E equals to rho all charges over epsilon naught, and del dot B equal to 0, and del cross E equals minus dB dt, and del cross B is mu naught J plus mu naught epsilon naught dE dt. Okay, now say we want to know what happens. This what Maxwell asked. Okay, if I have empty space, means this is equal to 0 and this is equal to 0. Of course, one solution of this thing is E is 0, B is 0, and then the entire thing is consistent. So like one solution is E is 0 and B is 0, and then nothing, the empty, the no electric field, no magnetic field. However, there is a this is not the only solution. That's what very important part is. These things have a more interesting solution. It's a solution where electric and magnetic fields can move in waves, a particular kind of electric and magnetic field, and they will have a relationship. Electric field and magnetic field will be related, and they will move. So let's just quickly carry out the argument. So you can see that I can I can just do over here like you have a dv/dt. So let's just do I want to get a so if I hit this guy with del cross, get curl of this, so del cross E will be minus del cross dB dt, but this is space this time derivative, so this will be same as d dt of del cross B. So I can actually use this now to eliminate you have a minus d dt mu naught epsilon naught dE dt, and so this is universal constant, both of them, so they're not varying with time. D square E dt square. So now this guy, you just do the del cross of E, and you're going to be able to expand that. Okay, so you have a del of del dot E, this left side equals to that, and then I use this, I can use that, and so that goes to 0, and so this whole equation, it just becomes minus del square E equals to minus mu naught epsilon naught d square E dt square, or you can say del square E equals mu naught epsilon naught d square dt square. So this is a wave equation for the vector field E, and you can do the same thing. Same thing will give you del square B equals to mu naught epsilon naught d square B dt square. Let me clean this up and talk about a little bit. But before we do that, let's look at what this actually this has three equations. You can say del square E of the x component, del square E of the y component, and del square E of the z component. If you write electric field as it's got x component I hat plus y component j hat plus z component k hat, and so the other side will be mu naught epsilon naught d square Ex dt square, and similarly. Okay, let me clean this up and then come back and talk about so what these equations do. Okay, so I recopied that. So you have these equations coming from Maxwell's, and they imply these. So whatever the solution of this must also obey that, right? So over here, if you look at the left hand side versus right hand side, so you have an electric field dimension over length square, and on the other side is dimension of mu naught epsilon naught electric field dimension over time square. So you can see already, if you bring this dimension on the other side, then or bring, better yet, bring this guy on the other side. So you have a mu naught epsilon naught. This dimension is 1 over length over time square. So so mu naught epsilon naught is actually it's the dimension of this, the square root of this is dimension of 1 over speed, and that's what turns out to be speed of light. We just multiply is 1 over square root of mu naught epsilon naught. So this is a wave. So this is a wave of electric field and a wave of magnetic field traveling at the speed of light. Waves of E and waves of B traveling at speed 1 over square root of mu naught epsilon naught. So if you plug in the values of mu naught and epsilon naught, so if you plug in mu naught epsilon naught, you get 1 over square root of mu naught epsilon naught is C. And this is what Maxwell said, okay, it's so close to the speed of light, then these are what the light is. Light is just electromagnetic waves. He was talking about the visible light, but then he noticed that these waves can have any frequencies, not just the frequencies limited to the speed of light or the wavelengths limited to the speed of light. It can have any other wavelengths. So this is a much more expanded view of what light can be. So light is a very small fraction of all the electromagnetic waves that are out there. Okay, so visible light, I mean the light that's our vision system is sensitive to. There are animals whose vision system is sensitive to maybe infrared light, or maybe so there are other organisms which are sensitive to other forms of electromagnetic waves. Ours is very sensitive to the vision system is sensitive to it processes the electromagnetic waves in a particular range of wavelengths, which we call visible light. Okay, one thing to notice is these waves. So these waves not only satisfy equation 1 and 2, but must satisfy these maybe just call it 0. All these 4 equations must satisfy this. Let's call it A, B, C, and D. So this is equation A, this equation B, this equation C, D. So you must obey also Maxwell's equations. They not just have to obey these guys, and that's gets lost in discussion. Sometimes people get wrapped up that this is what all there is, but this is not all there is. The wave are restricted by must obey. That's why this one says just electric field wave. This one says just magnetic field wave. But it doesn't say how the electric field and magnetic fields must be connected, must be related, and that's where this comes from. Okay, and we're gonna talk about that. Okay, let's move to the solution. So let's look at this. So space is infinite. Okay, we are gonna assume the infinite space so that we don't put where the but there's no place where the waves are generated, or where there's no place the waves are getting absorbed. This is just a very, you might say, just a mathematical problem, mathematical solution. So to do this, we will choose a coordinate system like x and y, and so these are and we will choose a wave to in this kind of and we'll chase the wave to travel along the z-axis. Okay, we'll see the one solution. A solution where we seek a solution where if I took a particular value of z, say some z0, and there is a xy parallel to xy plane, so this is xy plane at z equal to z0, that on this plane electric field has same value. Okay, so that kind of thing is called electromagnetic wave. So over E has same vector value at all points of this plane. So if you say I'm going to have such a simple answer like that, then that kind of thing has a it's called plane wave solution, and you'll see that this is a really very easy solution to work out, and the answer is going to be E will be E at any point x, y, z. So this has x, y, z, and t. So it's going to it's a multivariate, and it's going to be a some constant. So, and we can do cosine, and because we want to travel along the z, so we're going to do kz minus I'm going to define what the k and omega are, plus some kind of a constant. So this is some constant. All right, so if I pick a constant equals to pi over 2, then it will be all over. So there is this plane. Let me erase this. It's going to make it sign so you will know that much easier to follow. Okay, so if a constant is 0, if phi is 0, say phi equal to 0 case, in that case electric field, this value is going to be all 0 here. This is not necessarily 0, this is some constant vector in space. So E0 can be like that, is going to be E0 will still be pointed the same way. Okay, we're talking about E and E0. E is this field and E0 is just a constant vector multiplying a oscillating wave. So let's look at this, just take a sign so that we don't have to worry about this additional constant that comes in solution. You can put it in here. So what k is actually 2 pi over the wavelength, and what omega is a 2 pi times the frequency. Okay, so that's a k and that's omega. When you put it there, you'll find that. Let's put it in here and work it out. So you can see the E0 from both sides will cancel out. So this, to the left side, to take two derivatives, you're going to get minus k square. Okay, and the whole thing will just reappear. It's going to be E. The whole thing just comes out. X, Y, Z, T. Because taking two derivatives brings the sign back to the sign and picks a minus sign. And over here picks a minus omega and another minus omega. So you have a minus omega square over c square, and you have a E x y z t. So algebraically speaking, you can cancel this because it's arbitrary, and so you have a k. K omega over k equals to c. right? Omega over k equals to c. And I already said this is a, so this equation actually just said omega is 2 pi f. How do we know it's omega is 2 pi f? And this, that I'll just tell you just in a minute, but this is, just verify this, and this is 2 pi over lambda is c, and so this is same as lambda f equals to c. That's the equation we had earlier, right? Now let's just look at what these waves are and why this has to be that, why this has to be that. Okay, so looking at you know, at z equal to 0 plane, x and y here, so this is z equal to 0 plane. If you look at what you're gonna get, sine minus omega t, which is minus sine omega t. You plot it, you will see this is the time period. So time period is 2 pi over omega, and which is 1 over frequency, and so this is omega equals to 2 pi f. Now over here you look at time equal to 0 at all points along the z, and it's got, so we had as sine kz minus omega t. So if I put t equal to 0, I get sine kz, and then if I look at repeat, so this is the repeat distance, so this must be equal to wavelength. So 2 pi over k equal to wavelength, so the k has to be 2 pi over lambda. Then there are names for these things. K is called wave number. Now there is a little bit of problem with chemist people. Some older, maybe not older, maybe some other places. Physics people don't do this. Not physics. You're not in physics. K is 1 over lambda, and that just, we're not going to do that. We just k is 2 pi over lambda. And this omega is this is the frequency, which unit is hertz, 1 over second, etc. Okay, cycles per second. So omega is actually angular frequency, and from here this is radian, so you might say it should be radian per second, but this is hardly used. It's just a 1 over second. Okay, okay, so we can say that same way we get this solution from this. So we also have a similar solution. It's just you're gonna have different, these are the two constants. You have a vector for this, and then the constants phase. These are called phase constant, and this entire thing is called phase of this wave, phase of the wave, of the E wave, and this will be the phase of the B wave, and this will be called phase constant of B wave. Okay, so we haven't completed the solution. This is actually one step, but we need to make sure that these solutions also obey the Maxwell's equation. So this solutions, this solution put in the Maxwell equation, they also satisfy that. So this 1 and 2 must also satisfy Maxwell equations. Okay, so let's look at number 1. Okay, so this is the thing we're looking at, and this wave is traveling along the z direction. This will be traveling along the positive z direction, because these guys have opposite signs. Okay, so let's look at del dot E. What del dot E tells me must be equal to 0. So when I do the del dot E, of course, del dot E will be dz ez, right? Okay, dx ex plus dy ey plus dz ez equal to 0, and these have to be function of x y z t, function of x y z t, and this is a function of x y z t. But when we look at it, the way we have written down is not a function of x. So this is kills it, this kills it. So this is the only one that survives. And you do this out and you say, you notice that dz, so you have e0 e0k sine, sine becomes cosine kz minus omega t plus phi e equal to 0. This e0z, just the z components. So this one is e0z sine kz minus omega t plus phi e, and these guys are e0y sine kz minus omega t plus phi e, and similarly for this guy. So here this guy does not have any y, and that's why that got canned, you know, that went to 0. And this thing has a z here, so we say k is not 0, that's the wavelength is not 0 for this thing. So this part is not 0. Cosine can be 0 sometimes, but not always. So that will means e0z has to be 0. So we found out this vector cannot have z component. So it says e0 can only be e0xi hat plus e0y j hat, and this can be actually z and t. This can depend on z and t. That's what we have just written down, z and t for us. Could be in general, could depend on x, y, z, and t, but we are working with just z and t. So this is a function of z and t, this is a function of z and t, but the z component is absent, plus 0. So that's one conclusion, del dot e equal to 0 gives me. Okay, let me. Okay, so similarly, that we have for this, we have for the b. We can. So these are two done. How about this guy? Let's go del cross E. So del cross E. Okay, so when we do del cross E or del cross B, either of these two equations, when we plug into them, so they give you the same thing. And when you process it, the way you process it is. This is the only derivative that's going to survive for us because we've chosen to be along the z-axis. We've chosen that at any z is the same value. That's a plane wave, right? I explained earlier. So you just keep what going to be non-zero when you expand this in del cross, and then you work this out derivative carefully, and you are going to. So that's going to be left hand side is going to be this, and on the right side is minus dB dt. So it's going, because omega is going to bring a minus sign, it's going to kill that minus sign, and so we have this we're going to get, and then just equating this components along the x-axis and with the x-axis in both vectors. So along the x-axis we get, along the y-axis we get this, and using omega over k equals to c. So so using C equals to omega over K, you can see the B0x component is related to the Y component electric field, and the Y component magnetic field is related to negative X component electric field. So looking at, let me erase and just come back to it to explain the meaning of these things. Okay, so another thing that I forgot to mention is, furthermore, phi E has to be equal to phi equals to phi B. So if you set one to 0, the other will be 0. Okay, so let's set phi equal to 0. That just means electric field and magnetic field, E equal to 0 and B equal to 0 when it's over here, but it could be something over here, right? So I'm going to say this is, say the electric field is along the, meaning of this will be some electric fields along the X, or say Y axis. So if electric field is along the X axis, and then so this should be exactly opposite. This should be minus here and the plus here. I don't know where my mistake is, but if the electric field is along the X axis, so say this is the electric field, 0. So in that case, if E0 is E0 X only, I hat, if then the magnetic field B0 is going to B0Y J hat is going to be pointed that way. So magnetic field will be pointed that way. And over here is going to be the same way. Electric field will be pointed that way, and magnetic field will be pointed that way. So what's going on here is, this is the constant vector. This is the constant vector. How about this whole electric field? Now electric field over here could be anywhere in this direction. So if I'm sitting there, if I'm sitting there at z equal to 0, plane, I'm sitting there, then I will find the wave, the amplitude of the electric field. The electric field maybe go up, goes to some point, this much value. Let's call it E0 I hat. So it goes to E0 value, and then it start to come down, opposite direction. So this is the x-axis, and this is the negative x-axis, and it's going to be negative. And so it's going to oscillate up and down along this direction. And similar thing for the B. For the B magnetic field is going to go this way, and then start to come back, go same amount other direction, come back. So it's going to oscillate along this direction, and the E electric field will be oscillating along that direction. But they will oscillate in phase. That's what this means. They're going to oscillate in phase. So at the moment the E hits E0, at that moment B will hit B0. So the timing will be very perfect. When E electric field is 0 here, magnetic field is 0. So they're actually oscillating in sync. So this just means in sync. Okay, both electric and magnetic fields are in sync with each other. And this says when one is 0, the other is 0. Well, I could have taken electric field at some other direction, not just x-axis. Then what does this say? This says they're off by 90 degrees, right? So that if I look in xy plane, so this is XY plane at any point. So if I have a let me try. So what we are finding is if the electric field is this way, if the electric field is this way, then the magnetic field is kind of corresponding 1/c. So not the same scale. Let's see, electric field is way out here, and so this is then 1/c of the electric field. That's the B is that way at that point. So so the B is going in that direction and E is going in that. They're not. You can't add E to B. Okay, they're different things. So the B is going this way and E is going this way. Now, how about if I have, so this is the x-axis and this is the y-axis. So if I have electric field is this way, then magnetic field will be because the wave is coming towards us, z direction. You can always use right hand rule, and magnetic field will be pointed this way, and the ratio of them will be C. B will be equal to E/C. You say, wait, these are the axis on the axis. How about some other place? Suppose I have X and Y. How about if I have E in that direction? Let's put E in that direction. Well, then I just go 90 degrees ahead of that and will be so as if you go from E to B and Z is coming out. So and that's for when these two have opposite signs, which means it's coming towards the Z-axis. Okay, it's moving towards the Z-axis. So this is the plane wave solution. Now energy flow. This video has become very long, so I'm going to stop it, and we're going to start from energy flow, Poynting vector, etc. in another video. Okay, so see you another video. If you like this kind of deep explanation, you may want to hit the like button, and maybe you want to subscribe it. I'm going to post a whole bunch of it. I'm going to do some difficult problems. There are some simple problems people ask, given just a relationship between omega and z, and the value of this, etc. But that's not very interesting. You should. A more interesting thing is how this plays out in trying to explain other phenomena such as interference of waves, diffraction of waves. Those are other really interesting phenomena that you can't study without actually learning about what the waves are made up of and how to think about them. Okay, so we will talk at another time. Take care. Bye.